What's worse for the environment, your car or your phone? Statistics on the production of energy are fairly uh, reliable, accurate, accurate statistics on the consumption of energy by major sectors are harder to come by, and data on the energy consumed in the production of specific goods are even less reliable. Such energy embodied in products is part of the environmental price we pay for everything we own and use. The estimation of the embodied energy of finished goods relies not only on indisputable facts. So much steel in a car, so many microchips in a computer, but also on the inevitable simplifications and assumptions that must be made to derive overall rates. Which model of car, which computer or phone. The challenge is to select reasonable representative rates. The reward is to get a new perspective on the man-made world. Let's focus on mobile devices and cars. Mobile devices, because they are the primary enablers of instant communication and boundless information. Cars because people still want to move in the real world. Obviously, a car weighing 1.4 tons, about as much as a Honda Accord LX, embodied more energy than the 140 grams of a smartphone, say a Samsung Galaxy. But the energy gap is nowhere near so great as the 10,000-fold difference in mass. In 2020, worldwide sales of cell phones should be about 1.75 billion, and those of portable computing devices, laptops, notebooks, tablets should be on the order of 250 million. The aggregate weight of these devices comes comes to about 550,000 tons, assuming conservatively an average embodied rate of 0.25 gigajoules per ton. 4.5 gigajoules per laptop, and 1 gigajoule for a tablet. The annual production of these devices requires about 1 exajoule, 10 power 18 joules of primary energy, that is roughly equal to total annual energy used in New Zealand or Hungary, with little than 100 gigajoules per vehicle. The 75 million vehicles sold in 2020 embody about 7 exajoule of energy, slightly more than Italy's annual energy use, and weigh about 100 million tons. New cars thus weigh more than 118 times as much as all portable electronics, but require only 7 times as much energy to make. And as surprising as that may be, we can make an even more startling comparison. Portable electronics don't last long, on average just 2 years, and so the world's annual production of these devices embodies about 0.5 exajoules per year of use. Because passenger cars typically last for at least a decade. The world's annual production embodies about 0.7 exajoules per year of use, which is only 40% more than portable electronic devices. I hasten to add that these are necessarily only highly approximate calculations, but even if these raw aggregates were to err in opposite directions, that is, if cars making actually embodies more energy than calculated and electronic production needs less, the global totals would still be surprisingly similar, with the most likely difference no greater than twofold. And looking ahead, the two aggregates might get even closer. Annual sales of both cars and mobile devices have been recently slowing, but the future looks less promising for internal combustion engines. Of course, operating energy costs of the two classes of these highly energy intensive devices are vastly different. A compact American passenger car consumes about 500 gigajoules of gasoline during a decade of its service, 5 times its embodied energy cost. A smartphone consumes just 4 kilowatt hours of electricity annually, and less than 30 gigajoules during its 2 years of service, or just 3% of its embodied energy cost if the electricity comes from a wind turbine or from a photovoltaic cell. That fraction rises to about 8% if the energy comes from burning coal, a less efficient process. But a smartphone is nothing without a network, and the cost of electrifying the net is high and rising. Forecasts disagree about the coming rate of increase or about possible stabilization by using innovative designs, but in any case, those tiny phones leave quite an aggregate footprint in the energy budget and the environment. Who has better insulation? First impressions led to wrong conclusions. I well remember receiving a friendly welcome at the residence of a European ambassador in Ottawa, and in the very next sentence being thought that this house was perfect to withstand Canadian winters because it was made of real brick and stone, not like those flimsy North American wooden things with hollow walls. My hosts then swiftly moved to other matters, and in any case, I did not have the heart to belittle the insulating qualities of their handsome home. The error is easy to understand understand, but mass and density are better indicators of stardiness than of insulating capability. A brick wall obviously looks more substantial and protective than a wall with narrow wooden studs and covered on the outside with a sheet of thin plywood and aluminium siding, and on the inside with vulnerable gypsum and drywall. Angry European men do not make holes in bricks walls. Decades ago, when oil sold for $2 a barrel, most pre 1960 North American houses usually had nothing more to keep out the cold than the air space between the plywood and drywall. Sometimes the space was filled with wood shavings or shredded paper. Yet remarkably, even that feeble combination provided a bit more insulation than solid brick. The insulating value or thermal resistance is measured in terms of R value. It depends not only on the composition, thickness, and density of the insulation, but also on the outdoor temperature and moisture. A framed wall from 1960 had roughly the following R values: aluminium siding 0.6, thin plywood 0.5, air space 0.9, and drywall 0.5. That all adds up to 2.5, but standard brick 0.8 plastered on both sides offered no more than 1.0. Hence even a flimsy mass-built North American wall, insulated at least twice as well as Europe's plastered bricks. Once energy prices began to rise and more rational building codes thoughts came into effect in North America. It became compulsory to incorporate plastic barriers and fiberglass beds, pillow-like rolls that can be picked between the wooden frames or studs. Higher overall values were easily achieved by using wider studs, 2x6, or better yet, by double studding, which involves building a sandwich from two frames, each one filled with insulation. In North America, a softwood 2x6 is actually 1.5 by 5.5 inches or 38 by 140 millimeters. For a well-built North American wall, this means adding insulation values or drywall 0.5, polyethylene vapor barrier 0.8, fiberglass beds 20, fiberboard sheeting 1.3, plastic house wrap Tyvek thermal wrapped at 5, and beveled wood cladding 0.8, adding the insulating value of interior air film brings the total R value to about 29. Brick walls too got better. To keep desired outer look of colored brick. An old wall can be retrofitted from the inside by putting wooden battens thin strips that hold insulation in place on the interior plaster, and attacking insulation backed gypsum board integrated with a vapor membrane to keep out moisture with 2-inch insulated plaster board. This will triple the previous overall R value, but even so, the insulated insulated old brick wall will remain an order of magnitude behind the 2 by 6 framed North American wall. Even people who are generally aware of our values do not expect to see such a large difference. However, all this wall insulation can reach its potential only if the windows don't bleed heat. See the next chapter. Triple glazed windows, a see-through energy solution. The cast for untested technical fixes is the course of energy policy. Take your pick: self-driving solar-powered cars, inherently safe nuclear mini reactors, or genetically enhanced photosynthesis. But why not start with what is proven? Why not simply reduce the demand for energy, beginning with residential and commercial buildings, both in the United States and in the European Union. Buildings account for about 40% of total primary energy consumption. Transportation comes second at 28% in the US and about 22% in the EU. Heating and air conditioning account for half of residential consumption, which is why the single best thing we could do for the energy budget is to keep the heat in or out with better insulation. The most rewarding place to do that is in windows where the energy loss is the highest. That is to say, it has the highest thermal transmittance measured in watts passing through a square meter of material divided by the difference in temperature in kelvins on either side. A single pane has a heat heat transfer coefficient of 5.76 watts per square meter per degree of Kelvin. A double pane separated by 6 millimeters. Air is a poor conductor of heat, has a coefficient of 3.3. Applying coatings to minimize the passage of ultraviolet and infrared radiation, lower it to between 1.8 and 2.2, and filling the space between the panes with argon in order to slow down heat transfer. Chops it to 1.1. Do that with triple glazed windows, and you drop to between 0.6 and 0.7. Substitute krypton for argon, and you can get it down to 0.5. And that's a loss reduction of up to 90% compared to a single pane. In the world of energy savings, there are no other opportunities of that magnitude applicable on a scale of billions of units. Bonus point, it would actually work. And there is also a comfort factor with the outdoor temperature at minus 18 degrees Celsius. Common January overnight lows in Edmonton, Alberta, or daily highs in Russia's Novosibirsk, and the indoor temperature at 21 degrees Celsius. The internal surface temperature of a single pane window is around 1 degrees Celsius. An older double pane window will register 11 degrees Celsius, and the best triple glazed window 18 degrees Celsius. At that temperature, you can sit right next to it, and triple painted windows have the added advantage of reducing condensation of the interior glass by raising its temperature above the dew point. Such windows are already common in Sweden and Norway. But in Canada, with its low-cost natural gas, they may not be mandated before 2030, and as in many other cold cold weather jurisdictions, the required standard is still equivalent to just a double glazed window with one low emissivity coating. Cold weather countries have had a long time to learn about insulation. Not so in the warmer places, which need it now that air conditioning is becoming widespread. Most notable in rural China and rural India, single panes are still the norm. Of course, the temperature differential for hot weather cooling is not as large as in higher latitudes for heating. For instance, at my home in Manitoba, Canada, the average hour-night lows in January are minus 25 degrees Celsius, enough to make a difference for 40 degrees Celsius, even when the thermostat is turned down for the night. On the other hand, air conditioning in many hot and humid regions runs for much longer periods than does heating in Canada or Sweden. Physics is indisputable. But economics rules. Although triple glazed windows may cost just 15% more than double panes. Their payback times are obviously longer, and it is commonly claimed that the step from double to triple design is not justified. That may be so if you ignore improved comfort and reduced window condensation, and above all the fact that triple panes will keep reducing energy use for decades to come. Why then do we visionaries want to pour money into arcane conversion technologies that may not even work, and which, even if they did, would likely have bad side effects on the environment? What's wrong with simple insulation? Improving the efficiency of household heating. If our climate models are correct, and if we must indeed limit the increase in global warming to 2 degrees Celsius and preferably to just 1.5 degrees in order to avoid the serious consequences associated with the planet-wide temperature rise, then we will have to take many unprecedented steps to reduce carbon emissions. Attention commonly focuses on new techniques that result in higher efficiencies like light emitting dyes, or that introduce entirely new modes of energy conversion, such as electric cars. Conservation is in principle a more practical solution, but unfortunately, besides, as we have seen, triple glazed windows, there are few ways to extend it to what has long been the single biggest energy hog in the colder parts of the world: house heating. About 1.2 billion people need to heat their houses. About 400 million people living in the EU, Ukraine, and Russia. Another 400 million people in North America living outside the US, South and Southwest, and 400 million Chinese in the northeastern, northern, and western regions, and almost everywhere you look, the best available techniques are already as efficient as is practically possible. It is striking just how rapid the diffusion of efficient systems has been. During the 1950s, my family heated our house near the German border with wood burned in heavy cast iron stoves. The efficiency of this process is no higher than 35%. The rest of the heat escapes through a chimney. During my studies in Prague in the early 1960s, the city was energized by brown coal, a low quality lignite, and the stove I stocked had an efficiency of 45 to 50%. In the late 1960s, we lived in Pennsylvania on the upper floor of a small suburban house whose old furnace burned oil with about 55 to 60% efficiency. In 1973, our first Canadian house had a natural gas furnace rated at 65%, and 17 years later, in a newer, super efficient home, I installed a furnace with 94% efficiency. I eventually had it replaced with a model rated at 97%, and my progress through a succession of fuels and efficiencies has been replicated by tens of millions of people in the northern hemisphere. Thanks to North America's cheap natural gas and to the combination of more expensive but readily available Dutch, North Sea, and Russian gas in Europe. This, the cleanest of all fossil fuels, is what most of the people in northern climates have come to rely on in place of wood, coal, and fuel oil. In Canada, the production of mid efficiency 78 to 84% furnaces ended in 2009, and all new houses are now mandated to have high efficiency, at least 90% furnaces. The same will soon be true elsewhere in the West, while rising gas imports are already causing China to shift its heating from coal to gas. Future efficiency gains will have to come from somewhere else. Better insulation of the outer facing part of the house, especially better windows, is the obvious, albeit often expensive first step. Air source heat pumps transferring heat via a heat exchanger have become popular in many places and are effective as long as temperatures do not dip below freezing. In cold regions, they still need winter backup. Solar heating is possible too, but it doesn't work very well where and when it's needed most in very cold climates during prolonged spells of cold but overcast weather during blizzards and with the solar modules and the heavy snow cover. Will the long-term need to limit global warming eventually lead to something unthinkable? I'm referring to the most economically sensible choice, and the one that would make the greatest, longest lasting contribution to reducing the carbon burned of heating, limiting the size of houses. We could do away the McMansions mass-built houses with masses of floor place in North America. Doing away with similar houses in the tropics would save on the opposite expense on energy currently wasted on air conditioning. Who is up for that? Who's up for that? Running into carbon. In 1896, Sven Arrhenius of Sweden became the first scientist to quantify the effects of man-made carbon dioxide on global temperatures. He calculated that doubling the atmospheric level of the gas from its concentration in his time would raise the average mid-latitude temperature by 5 to 6 Celsius. And that's not too far from the latest results obtained by computer models running more than 200,000 lines of code. The United Nations held its first framework convention on climate change in 1992, and this was followed by a series of meetings and climate treaties. But the global emissions of carbon dioxide have been rising steadily, just the same At the beginning of the 19th century, when the United Kingdom was the only major coal producer, and global emissions of carbon from fossil fuels combustion were minuscule at less than 10 million tons a year. To express them in terms of carbon dioxide, just multiply by 3.66. By centuries, and emissions surpassed half a billion tons of carbon. By 1950, they had topped 1.5 billion tons. The post-war economic expansion in Europe, North America, the USSR, and Japan, along with the post-1980 economic rise of China, quadrupled emissions thereafter to about 7 billion tons of carbon by the year 2000. In the 2 centuries between 1800 and 2000, the transfer of carbon from fossil fuels to the atmosphere increased 650-fold, while the population had increased only sixfold. The new century has seen a significant divergence. By 2017, emissions had declined by about 15% in the Europe Union, with its slower economic growth and aging population, and also in the United States, thanks largely to the increasing use of natural gas instead of coal. However, all these gains were outbalanced by Chinese carbon emissions, which rose from about 1 billion to about 3 billion tons, enough to increase the worldwide total by nearly 45% to 10.1 billion tons. By burning huge stocks of carbon that fossilized ages ago, human beings have pushed carbon dioxide concentrations to levels not seen for about 3 million years. Through drilling deep into glaciers covering Antarctica and Greenland, we can recover slender tubes of ice that contain tiny bubbles, and as we drill deeper, increasingly older ice, by sampling the air locked in those tiny bubbles, we have been able to reconstruct the history of carbon dioxide concentrations going back some 800,000 years. Back then, the atmospheric levels of the gas fluctuated between 180 and 280 parts per million, that is from 0.018 to 0.028%. During the past millennium, the concentrations remained fairly stable, ranging from 275 ppm in the early 1600s to about 285 ppm before the end of the 19th century. Continuous measurements of the gas began near the top of the Mauna Loa in Hawaii in 1958. The 1959 mean was 316 ppm. The 2015 average reached 400 ppm, and 415 ppm was first recorded in May 2019. Emissions will continue to decline in affluent countries, and the rate at which they grow in China has begun to slow down. However, it is speeding up in India and Africa, and hence it is unlikely that we will see any substantial global declines anytime soon. The Paris Agreement of 2015 was lauded as the first accord containing specific national commitments to reduce future emissions, but actually only a small number of countries had specific promises. There is no binding enforcement mechanism, and even if all of those targets were met by 2030, carbon emissions would still rise to nearly 50% above the 2017 level, according to the 2018 study by the Intergovernmental Panel for Climate Change. The only way to keep the average world temperature rise to no more than 1.5 degrees Celsius would be to put emissions almost immediately into a decline steep enough to bring them to zero by 2050. That is not impossible, but it is very unlikely. Reaching that goal would require nothing short of a fundamental transformation of the global economy on scales and at a speed unprecedented in human history, a task that would be impossible to do without major economic and social dislocations. The greatest challenge would be how to lift billions from poverty without relying on fossil carbon. The affluent world has used hundreds of billions of tons of it to create its high quality of life, but right now we do not have any affordable non-carbon alternatives that could be rapidly deployed on mass scale in order to energize the production of enormous quantities of what I have called the four pillars of modern civilization: ammonia, steel, cement, and plastics, which will be needed in Africa and Asia in the decades to come. The contrasts between the expressed concerns about global warming, the continued release of record volumes of carbon, and our capabilities to change that in the near term could not be starker. Epilogue. Numbers may not lie, but which truth do they convey? In this book, I have tried to show that we often have to look both deeper and wider, even fairly reliable, indeed even impossibly accurate numbers need to be seen in wider contexts, and informed judging of absolute values requires some relative comparative perspectives. Rigid ranking based on minuscule differences misleads rather than informs. Rounding and approximation is superior to unwarranted and unnecessary precision. Doubt, caution, and incessant questioning are in order, but so is the insistence on quantifying the complex realities of the modern world. If we are to understand many unruly realities, if we are to base our decisions on the best available information, then there is no substitute for this pursuit.